So, let's talk about quantum physics. It is, without a doubt, the most successful scientific theory we've ever come up with. And you know what? It's also the weirdest. It's the operating system for the entire universe, from the teeniest little particles to the absolute biggest monsters out there in the cosmos. So, how does it all work? And, more importantly, why should you care? Well, let's dive in and try to decode this stuff.
Okay, but first, a little heads up. Quantum physics is, well, it's strange. It really doesn't care about our common sense, and it's going to challenge everything you think you know about reality. So, if at some point your brain starts to feel like it's doing gymnastics, don't worry. That's a totally normal side effect when you're peeking behind the curtain of the cosmos. You'd probably think that a story about the smallest things in existence would start with, small things. But nope, we're going to start with the biggest, meanest, most terrifying monsters in the entire universe. I am, of course, talking about black holes. These are objects so incredibly massive, they literally punch holes in the very fabric of space-time. I mean, even the great Albert Einstein, the guy whose own theories predicted them, thought they were just too wild, too crazy to actually exist.
Their gravity is just so powerful that once you cross that line, the event horizon, the point of no return, that's it. Nothing gets out. They can swallow whole planets, entire stars, without so much as a burp. They are, for sure, the ultimate bullies of the cosmos.
And yet, these monsters, these seemingly unbeatable giants, they have a fatal flaw, a secret weakness. And believe it or not, the person who first spotted this was none other than Stephen Hawking. He realized their doom wouldn't come from something bigger, but from the strange rules of the quantum world itself. So how in the world does the tiniest stuff in the universe take down the biggest? Well, it's a process we now call Hawking radiation. See, it turns out that empty space isn't really empty at all. It's just fizzing with these little pairs of virtual particles that pop into existence and then disappear in a flash. But right at the edge of a black hole, one particle can fall in while its partner escapes. And that escaping particle, it has to steal a tiny, tiny bit of the black hole's energy to become real. And so drip by drip, over literally eons, this little quantum trick makes the monster just evaporate away. Okay, so quantum physics can kill black holes. That's pretty cool, I'll admit. But what does any of that have to do with us here on Earth? Well, as it turns out, pretty much everything. We're not waiting for a quantum age. We are living in it right now.
I mean, this isn't some sci-fi thing we're talking about here. The tiny transistors inside the computer or the phone you're using to watch this, they only work because of quantum mechanics. That GPS that tells you where to turn, the lasers that scan your groceries at the checkout, the fiber optic cables that are the backbone of the internet, all of it, every single bit, is built on our mastery of this incredibly strange realm.
And that's really the key takeaway here. Quantum physics isn't just some abstract theory for scientists in a lab to debate. It is the fundamental operating system of our modern world. If you want to understand the 21st century, you've got to get a handle on this.
All right, so now that we've established why you should care, let's wade into the deep, weird waters. It's time to actually look at the bizarre rules that run this quantum world, a world that made even a genius like Einstein deeply uncomfortable.
See, before quantum mechanics, physics was, well, predictable. Think of it like a giant clockwork machine, the kind Isaac Newton described. If you knew exactly how you threw a baseball, you could calculate exactly where it would land. No surprises. But the quantum world? It just throws all that certainty right out the window. It's a world built on chance, on probability. You can know everything there is to possibly know about a particle and still only be able to say, well, there's a 50% chance it'll do this and a 30% chance it'll do that. It's the very thing that made Einstein so mad, leading to his famous line that God doesn't play dice. Well, turns out he might.
And this is where reality just completely unravels. Get this, before we actually look at a quantum particle, it doesn't have one specific location. It exists in something called a superposition, which is like a ghostly cloud of all its possible locations all at the same time. It's not here or there, it's kind of everywhere and nowhere all at once. The very act of us looking at it, of measuring it, forces the particle to choose to snap into just one single position. It's almost like our looking at it creates the reality we see.
So what does that actually mean? Is the particle literally in all those places at once, or is it just nowhere until we look? And here's the kicker. Quantum theory itself doesn't give us the answer. That's one of the deepest, most profound mysteries we are still wrestling with today.
And if you thought that was weird, hold on, because now we've got entanglement. This is what happens when two particles get linked together so deeply that they basically act like one single object, even if you put them on opposite sides of the galaxy. If you measure something about one particle, say its spin, you instantly know the spin of its partner, faster than the speed of light.
This instantaneous connection was so bizarre, so completely against everything he believed about how the universe should work, that Einstein just couldn't stomach it. He famously, and kind of dismissively, called it spooky action at a distance. But here's the thing. Experiment after experiment has proven that, spooky or not, entanglement is 100% real.
Okay, so we've got these totally bizarre rules. Things are just probabilities. They can be in many places at once. They have these spooky connections. But here's the thing. These aren't just thought experiments for philosophers. These are the actual blueprints we've used to build some of the most incredible tools in human history.
All right, look at this insane number on the screen. That is the exact number of times the energy in a cesium atom wobbles back and forth that we have all agreed to officially call 1 second. Atomic clocks use these super predictable quantum jumps inside atoms to keep time with a precision that is just staggering. And it's that insane level of precision that makes the GPS in your phone actually work.
And this is the real power of quantum control. Let's use an analogy here. A regular light bulb, that's quantum chaos. It's like a stadium full of people all singing different songs, totally out of tune. The light particles, the photons, are just flying everywhere. But a laser? Oh, a laser is a quantum masterpiece. We've figured out how to get trillions upon trillions of photons to march in perfect lockstep. Same color, same phase, same direction. It's like a perfectly disciplined choir, all singing one single pure note. And we can take that incredible quantum control and do something that sounds like pure science fiction. We can listen to the universe itself. At an observatory called LIGO, they take one of those perfect lasers and split it in two, sending the beams down these long tunnels. They're set up so that when the beams come back together, they perfectly cancel each other out, creating total darkness. But when a gravitational wave from, say, two colliding black holes washes over the Earth, it stretches one tunnel and squeezes the other by a distance smaller than an atom. And that tiny change is enough to throw the lasers out of alignment, so they don't cancel anymore. And that tiny little flicker of light is the signal that we've just detected the universe shaking.
So look, we've already used quantum physics to build our entire modern world, but honestly, we're just getting started. The next great technological revolution is already brewing, and you guessed it, it's built on these very same strange quantum principles.
You know how our computers work, right? They're all built on bits, tiny little switches that are either on or off, a 0 or a 1. Simple. A quantum computer uses a qubit, and because of superposition, a qubit can be a 0, a 1, or a mix of both at the same time. This one little trick opens up a computational space that is just mind-blowingly vast. But then, when you use entanglement to link these qubits together, oh man, the power just explodes. To put it in perspective, the physicist John Preskill calculated that if you wanted to just describe what was happening with a few hundred entangled qubits, you would need to write down more regular bits than there are atoms in the entire visible universe. That's the kind of power we're talking about. Now, let's get one thing straight. You are not going to be checking your email or playing video games on a quantum computer anytime soon. Think of them more like specialized tools designed to tackle a very specific set of problems that are just flat out impossible for even the world's biggest supercomputers. Things like designing brand new drugs from scratch, inventing new materials, or cracking the world's toughest codes.
So, from the death of black holes to the GPS in your pocket, and all the way to the future of computing, the quantum world isn't just out there, it's everywhere. We've gone from being baffled by its weirdness to literally building our future with it. Which really just leaves you with one final, fascinating question. 50 years from now, what quantum technologies that we can't even imagine today will be a completely normal, everyday part of your life?